Welcome students. We are going to discuss about differences between linear and non-linear differential equations. So what kind of differences are we looking at? So we are looking at first two fundamental questions, namely the existence of the solution to a linear differential equation and a non-linear differential equation. And then we want to answer the question about uniqueness, whether the given solution is unique or not. So we all know that if we take, say, x squared plus 1 equals to 0, just because we write an equation over R doesn't mean it has a solution, right? So no solutions. So similarly, if I'm given a differential equation, there is no guarantee that there is a solution, okay? So let's ask these questions in details now. So question, does an IVP, which is the initial value problem, have a solution? Say y equals to phi of t. Then the second question is, if this such solution exists, if it exists, by it I mean the solution, is the solution unique? And if the solution is not unique, how can you guarantee that you have found out all the solutions? So if not unique, how can we know and find all the solutions? So first thing we'll deal in this case is we'll deal with the first order linear differential equations. They are easy to see and they are very predictable based on the light of our integrating factor method. Okay. Whereas for the first order non-linear differential equation, you'll see that it's less difficult. Sorry, it's more difficult and less predictable. What do I mean by that? The solutions are the existence of solution is not that easy to determine. Okay. So we'll see that in a minute, but let's first deal with the first order linear differential equation. So you're given a first order linear differential equation, which is of form y of t plus pty equals to g of t. So it should be y prime, right? This is what the first order differential equation is. Now, suppose p of t and g of t are continuous on an open interval I. Let that I be given by alpha to beta. And this I also consists of the initial value. So y of t naught equals to y naught. So this is where your initial value comes from. Okay. So let's read this again. So suppose that p of t and g of t are continuous on an open interval I given by this open interval alpha to beta, and it also consists of the point t naught. Then it says there is a unique solution or unique function y equals to phi of t that satisfies this differential equation along with the initial condition y of t naught equals to y naught. Yeah, where y naught is an arbitrary prescribed initial value. So if you look at this theorem, it tells you that the uniqueness, so the existence and uniqueness both are guaranteed just by p of t and q of p of t and g of t being continuous. Okay, so let's see why this is the case. So discussion of theorem in the context of the derivation of method of integrating factors. So we'll try to see how the method of integrating factor helped us to find or helps us to prove this theorem. So recall from section 2.1 of integrating factors, we saw that y of t is 1 by mu t integral mu s gs ds plus c with your initial condition. With the initial condition will determine initial condition determining c. Okay, so the initial condition will determine c. Now we can write, so setting the lower limit. So in this solution, if you set the lower in this integral, if you set the lower limit of integration to t naught, we have, well, we already have y of t naught equals to y naught. So therefore, you can write this as y of t equals to 1 by mu t integral t naught to t mu of s gs ds plus y naught, right? So now note the following. Mu of t is exponentiation of p of s ds, right? Or if you want to write it directly, mu of t as p of t dt e to the power this guy. We can see that mu of t is going to be greater than 0. Later on, when we discuss Abel's theorem, we'll see that why precisely mu of t is greater than 0. But this we have assumed earlier as well. Now, so from here, recall. So we want to show that this exists and is unique, right? Because this is our solution. So let's see why is that the case. So note that p of t, so since p of t is continuous, this integral is well defined, right? For continuous function, the integral exists, is defined. And not only the antiderivative is defined, it's also continuous. Sorry, it's continuous and differentiable. So mu of t is differentiable. This follows from the fundamental theorem of calculus 1, right? So we can see that mu of t y prime, so this exists, this is equal to mu t gt, right? This was a part of the step from the integrating factors. Right? So this implies, so these two are continuous. So this implies mu y prime. So because gt is continuous, mu t is continuous, therefore it's integrable. So therefore I can compute the antiderivative of this part here. So I get mu t is mu t prime. So this part is integrable because the right hand side is continuous. Continuous on where? On I. So this discussion is happening on I, is integrable, which means what? A solution exists. All right. So one solution exists. However, the y naught determines C uniquely, implies the solution is unique as well. The solution is unique. Now, so let's look at this theorem once again. So this theorem said to us following, that if you take a first order linear differential equation and your P of t and G of t both are continuous on an interval, some interval I, so let's say it's given by alpha and beta, then you can find a solution to this differential equation which satisfies y of t naught equals to y naught. This t naught should be from the interval I. Okay, so let's look at a problem now. Now, find the interval in which this initial value problem with y of pi equals to 0 has a unique solution. So first of all, we'll convert the differential equation into standard form. So convert d into standard form. So what does that amounts to? That would amount to dividing throughout by cos t. So we get y prime plus sine t over cos t equals to cos t over cos t, which is 1. I mean, of course, when I'm dividing by cos t, I'm removing all the points where, so, so all the points where the cos t was 0, right? So here, P of t is tan t and G of t is 1, is cos t over cos t, which is 1 for t naught whenever t does not becomes what? 0. So t is not equal to, so when does cos become 0? When it is not multiple of what? When it's not multiple of a pi, but it's not odd multiple of pi. So it's 2k plus 1 times pi. So when it's not odd multiple of pi by 2, my bad. Okay. So now, so this is the first part. So now, what does our theorem tells us? Our theorem tells us wherever P of t and G of t are continuous is where we'll find our intervals on which the solution is continuous, right? So let's determine the region of continuity of P of t and G of t. So both tan pi, tan t, and cos t, so cos t by t, which is your G of t, is continuous except when cos t equals to 0. Yeah, because after all, tan t is also sine t over cos t. Yeah. So that happens when, so the discontinuities are at t equals to n pi plus half pi or pi by 2, right? Which is exactly this thing written in a different format. So discontinuities are at t equals to pi plus pi by 2. So now out of this, we need to, so these are the discontinuities. So you can think about it in the following way. So discontinuities are at say minus pi by 2, then pi by 2, then 3 pi by 2, and so on. So recall, how does the tan graph looks like? So at, so these values are So at minus pi by 2 to pi by 2, this is how the tan graph looks like. These are the asymptotes. And then you have again, and this value is this is I. Okay, so this is how the values. So now, next thing we want to see is pick up the interval of continuity. So step 3, pick up the interval of continuity. Now the solutions exist in all these intervals, right? What are the intervals? So first interval is minus pi by 2 to pi by 2 in this interval. Then the second one in this interval. So in all these intervals, it's continuous, but which interval to pick? That is given by the initial condition. So initial condition is given at what? At y of pi equals to 0. So therefore, since pi lies in which interval? Pi lies in the interval pi by 2 to 3 pi by 2. Yeah, the initial value is y of t pi equals to y naught. The solution is valid in the interval pi by 2 to 3 pi by 2. Yeah, and we can say this even without computing the solution in this case, right? So does that make sense? Okay, so let's move ahead and talk about, so compare this case with the nonlinear differential equation. So again, let's start with, so we are investigating the first order differential equation. So the first order differential equation y prime equals to f of dy. Okay. So now suppose you're given that f and partial derivative of f with respect to y is continuous on some rectangle where t is between alpha and beta and y is between gamma and delta. So what does it mean? Let me draw this. So you have your t is between alpha and beta, and your y is between, say, gamma and delta. And this contains your initial, so you're given that this box here, this box contains your t naught, y naught, where you're given y of t naught equals to y. So what is the story? So let's repeat. What does it say? It says that if you're given f and dou f by dou y is continuous on some rectangle around t naught y naught, then there exists an interval around t naught. So if you look at t naught plus h, so t naught minus h to t naught plus h, if you take your y from here, sorry, if you take your t from here, then there'll be unique solution to this IVP. Okay. So it's not giving you the interval, but it's saying that there exists an interval which contains your t for which there is a unique solution. Okay. So let's discuss this. So clearly, this hypothesis, the hypothesis of the theorem, reduces to the previous theorem if this DE is linear. Now, let's see. So when can this differential equation be linear? When you have f of ty equals to minus pty plus g of t, right? So now if you take partial derivative of this, so dou f by dou y, partial derivative of f with respect to y, will get, so you take the partial derivative. So recall, how do you take a partial derivative with respect to y? So everything except y is treated as constant. So minus pt, the constant comes out, partial derivative of y with respect to y is 1, and partial derivative of g of t is 0 with respect to y. So therefore, this theorem tells us what? Let f be continuous on some rectangle, f and partial derivative of f with respect to y. So in this case, it will reduce down to saying f and partial derivative of y is continuous. So these are continuous, right? But this is same as saying if and only if p and g are continuous. Okay, so you see, if you have your f of ty is a linear differential equation, sorry, if f of ty is linear in y, then this theorem reduces to the previous case here, where the requirement was that p of t and g of t has to be continuous on some interval. Okay. So two, unlike linear case, this theorem guarantees the existence and the uniqueness, because after all, we are discussing those problems, right? The existence and the uniqueness problem, and the uniqueness in some interval t naught minus h less than t naught plus h. Which interval is that? What is the size of this interval? That is unknown. So in general, the value of h is unknown. Whereas in the case of linear differential equation, the value was exactly known, because all we needed to do was look at the interval in which p of t and g of t were continuous, and along with that, the interval where you consist of which contains t naught, the initial parameter at which your initial value is defined. Okay. So in general, the value of h is unknown. I mean, of course, there are some special cases where you can find it out, but in general, value is unknown. Third, the conditions in this theorem are sufficient for existence and uniqueness. But not necessary. What do you mean by that? Means we don't really need this to satisfy. So if these things are satisfied, like f and partial derivative of f with respect to y is continuous on some rectangle, and then we are guaranteed an existence and uniqueness of the solution. But existence and uniqueness of solution does not necessarily require that these have to be continuous in some rectangle. Same thing about the first one as well. For the first order linear differential equation, we do not necessarily need that these conditions are satisfied. What conditions? that your P of t and G of t are continuous on some open interval containing T naught. So these conditions are sufficient, but not necessary. All right. So fourth, so as you have already observed from the direction fields, as observed from direction fields, now if you look at the direction fields, you can tell about the uniqueness. Why is that? As observed from the direction fields, a consequence of the theorem, a consequence of this theorem is that the graphs or the solutions, basically, the graphs cannot intersect. Yeah, you can't have one direction field going like that and the other one direction field going like that. This is not allowed. Yeah. Otherwise, there is no, otherwise two solutions can be constructed with the same initial condition here. So if you call this as initial condition, you'll have two solutions, right? Which is not true. So that's the idea. All right, so let's apply this theorem of existence and uniqueness to a nonlinear first order differential equation and see what do we get with it. So first of all, we have y prime. So this is your y prime. This is your f of xy, which is x squared by y, with y of 0 to y naught. So now this is first order because the derivative, it's the first derivative. Non-linear because it's not linear in y. You see it's 1 over y. 1 over y is not linear in y. So now let's try to apply the existence and uniqueness theorem. So what do we need for, so f of xy, which is x squared by y, and partial derivative of f with respect to y is minus 1 by x squared. So x squared is a constant, it comes out. So derivative of, let me write that down. So x squared comes out, and then you're taking derivative of this with respect to y. Derivative of 1 over y is minus 1 over y squared, so it's going to be minus x squared by y squared. And this is continuous for what? For all y not equal to 0. Okay, so this means for some t naught, well, in this case you have x instead of t, so for some 0 minus h and 0 plus h, so for some x in here, we'll have what? A unique solution. So for this guy, we'll have the unique solution, right? So let's go ahead and do that. So this means, so therefore theorem tells us, so the theorem above tells us that first of all, it's defined, it's continuous for all y not equal to 0, right? So it says if your y naught is not 0, then there exists an interval minus x h within which your IVP, the given IVP here, has a unique solution. Note that we still don't know what this h is, so that has to be emphasized. We do not know h. All it says is that there is some interval around 0 in which if your x comes from that interval, your solution exists and is unique. Yeah. So now, what if you have y naught equals to 0? So if y naught equals to 0, then the theorem gives no information. No information whatsoever, right? So let's solve this differential equation. So we can see that this differential equation is separable. So we have dy by dx is equal to x squared y. So it's separable. So this gives us y dy equals to x squared dx. Integrate both sides, we get y squared by 2 equals to x cubed by 3 plus some constant c. So this gives me y square equals to 2 by 3 x cubed plus 2 c. Now I need to find out what is this constant of integration. So for that, notice that y of 0 is y naught. So therefore, when I put 0, I get y naught square equals to 2 by 3 times 0 cubed plus 2c. So therefore, c equals to y naught square by 2. I plug this back in this equation. So we get y naught square equals to 2 by 3 x to the power 3 by 2 plus y naught square. So this is your solution. Or if you take square root on both sides, so solving is to solve for y, and let's see, we get plus or minus 2 by 3 cubed to the power 3. Oh my bad, this is not 3 by 2, this is power 3, right? So power 3 plus y naught square. So this is your solution. Now out of this, we can understand about two cases that we can identify. So now note that when we have, so both the solutions satisfy the differential equation. So both solution satisfy differential equation. So then if both of them satisfy it, question comes to our mind is that is the solution unique, right? So you can check easily that both the solutions are satisfied. So you have, if you take y equals to plus or minus 2 by 3 x cubed plus y naught square, then dy by dx is going to be 1 by 2 by 3 plus or minus x cubed plus y naught square times derivative of inside with respect to x, which is going to be 2 by 3 times 3x square. So this 2 and this 2 will cancel, this 3 and this 3 will cancel. You will have, what do you have? You have, so let me just write it down properly. So this 2 and this 2 will cancel, this 3 and this 3 will cancel. So you're left out with what? You're left out with x square upon plus or minus 2 by 3 x cubed plus y naught square. So this is same as x square upon y. The parity depends on what original solution you chose. So you see both of them are solution. Yeah. But then what about the uniqueness case? Right. So let's investigate that. But before we go further, let's see. So this is both are solutions. So now when does the solution exist? So the solution, solution exists. The solution exists whenever whatever is inside the square root is well defined. That is same as saying 2 by 3 times x cubed plus y naught square is greater than 0. Why greater than 0? Because we are having x squared by y. So not only it's defined inside the square root sign, it has to be non-zero as well. So this happens when you simplify. You get 2 by 3x cubed equals to minus y naught square. And then if you simplify, you get x is greater than minus 3 over 2 y naught square, and then you take power 1 by 3. So the solution exists when x is bigger than this guy. Now, question, what about the uniqueness part? So we saw that there are two solutions, right? So uniqueness, is the solution unique? And if it is, it should be unique around some interval containing, by our theorem, it should be unique in some interval containing 0. What 0? X equals to 0. So for that, notice the following. If y naught is not 0, if y naught is not 0, then we have y naught, y of 0 is equal to 2 by 3. I'll put x equals to 0, so I get 0 cube plus y naught square. So this will give me y naught equals to square root of naught square with a plus or minus sign. Now both sides should agree, right? So the only solution is, so if your y naught was greater than 0, then the only solution is what? You need to take the plus sign because both of them should agree. So this sign should be chosen as plus. So then we have, so if y naught is positive, then we have y equals to 2 by 3 x y naught square is the unique solution. So you see how the initial value came to rescue about the uniqueness of the initial, so about the uniqueness of the solution. Okay. So now the theorem only guarantees, so of course, again, then this theorem guarantees a solution in an interval. What is the size of this interval? Of unknown size, right? Because in nonlinear, you can't define what size of interval in which the solution exists and is unique. Yeah, size, but we know that it should be inside this interval. So this is going to be minus 3 by 2 y naught squared to the power 1 by 3 less than x less than infinity. So we know that inside this interval, the solution exists and is unique. Right. Now, what about the second case when y naught is 0? So if y naught is 0, so let's go back to this and see y naught is 0. So if y naught is 0, then we get yx equals to 2 by 3 x cubed, and yx equals to square root of 2 by 3 x cubed with a minus sign, because then you can't use this to determine the sign, right? So this was, you could use this to determine the sign, but now you can't use that to determine the sign because this is 0. So there are solutions, and both give what? Give y of 0 equals to 0. So therefore the solution is not unique. Yeah, so you'll say, does this result opposes the theorem? And the answer is no, because when you look at this theorem, we already said that it will have all the solutions for it will be having unique solution only if y is not 0, right? So if y naught is 0, that means the value of y at that point is 0, and hence the solution is not unique. In fact, it basically makes the theorem more robust. Right. So you can see this from another word of caution is basically from GeoGebra. So here is the so here's the GeoGebra of the differential equation we just now saw. So as you see, it has one solution all the time, but at y0 equals to 0, that means same as I have basically relabeled y0 as c in this case. So y0 equals to 0. There are actually two solutions, one which goes upward and the other one which goes downward. However, GeoGebra does not basically shows those solutions. All right. So so GeoGebra doesn't find all the solutions. All right. So this is one of the dangers of using the software to compute solutions of ODE blindly, right? That it will not show all the solutions, right? So now let's apply the previous result, previous theorems, two theorems to this IVP. So what do we have? We have dy by dx equals to y square, where y0 is equal to y naught. So first question, what kind of differential equation is it? This is first order, clearly, because we have dy by dx, but is it linear or non-linear? So as you can see, because we have y square, your f of xy is, so you have y prime equals to f of xy. This is not linear in y, so therefore this is non-linear. First order ordinary differential equation. Okay, so that is that. So now we need to basically apply the theorem. So recall what are the conditions for the theorem. So you needed f of xy, which is y square, and dou f, partial derivative of f with respect to y, which is 2y, to be continuous, right? But they both are continuous, for all values of y. This implies what? There exists a unique solution where unique solution in some interval around 0, right? In some interval around 0. So y 0 minus h, which is minus h, 2 plus h, right? Because the idea is that the solution exists if you're given y of x naught equals to y, then the solution exists for all here, but in this case, our x naught is 0. Okay, so let's find it out. So again, this differential equation is separable. So we have dy by dx equals to y square implies dy by y square equals to dx, integrate on both sides. This gives me minus 1 by y equals to x plus c. Or if I want to solve for y, so I can see that minus 1 upon x plus c equals to y. All right. And now we are given initial condition that y of 0 is, so y of 0 is, on one hand, it is minus 1 by c. And on the other hand, we have y of 0 is y0. This is going to be y0. So therefore, we get what the differential equation becomes: y equals to minus 1 upon x plus. Now instead of c, what can I write from here? So c equals to minus 1 by y0. So of course, we need that y0 should not be 0. Otherwise, this is not. So we get equals to minus, we get x minus 1 by y0. Okay. So now you see this solution has a singularity. Why does it have singularity? Because yx is undefined when y0 is 0, right? So yx is undefined at what? At x equals to 1 over y0, right? Then you're dividing by 0. That doesn't make sense. So therefore, the interval of definition, so what can we say about the interval of definition? The interval of definition is excluding the intervals which exclude this point. So the intervals of definition or the interval of definition is minus infinity to x less than 1 by y0 if y0 is greater than 0 and 1 by y0 less than x less than infinity if y0 is less than. Okay. Now, unlike linear differential equation, the fact that solution has a singularity cannot be inferred from f of dy. So you see non-linear, so this is what we were saying in earlier on, that it is slightly more complicated to discuss solutions of linear non-linear first order differential equation because they come with their own problems like that. Whereas for linear differential equation, you could just look at the p of t and g of t to determine how the nature of solution is going to be. But for non-linear, as you see in this example, you have to basically find the solution to determine what is happening. Now the condition, so that's one important part to look at. The location of singularity depends completely on the initial condition. Again, this is unlike in the case of linear differential equation, right? In linear differential equation, you can find it out right away. So then the question is there a general solution to this differential equation? The solution, of course, is given by y of x equals to 1 upon x plus c. This looks like, so this looks like a general solution. But there are solutions that do not take this form. So first of all, if you're wondering what does a general solution means, is there a general form to the solution? Like, for example, this would have been a general solution if the first one, if by changing all the c's, I would have gotten all the solution. Yeah. But for this differential equation, we can have a solution dy by dx equals to 0 and y square equals to 0, which means dy by dx equals to y square. So this is a solution. So not all solutions to this differential equation are in this format. Okay. So let's have a summary of whatever we have discussed. So if you take linear first order differential equation, it has nice properties. The coefficient p and g are continuous. If they are continuous, then the general solution that includes all the possible solutions of differential equation is possible to create. The corresponding IVP has a unique solution. The uniqueness comes from the initial value. And the IVP has explicit solution of the following format, where mu of t is given by the following. And how do you determine the discontinuous points of your y of t? They are precisely the discontinuous points of p of t and g of t. So you see, y of t is uniquely determined by p of t and g of t. None of these statements are true about our non-linear first order differential equations. All right. So